So hello, this is Jai Mehta from Department of Mathematics, Sardar Patel University. So hello and welcome to the first lecture of group theory uh, of semester 3 course of Department of Mathematics, Sardar Patel University. So most of you have studied group theory in BSc, but that would be very basic, and this is an advanced course in group theory. But the first unit is kind of revision, and it might be possible that some of you may have studied some advanced topic in group theory in your BSc also. But we'll begin from the revision of group. So before we begin with the definition of group, just let us understand the significance of groups and applications. Group theory, as you know, groups are the very basic structure. The first thing is that groups are the basic abstract basic structure of abstract algebra. It's also known as modern algebra. Why this is the basic structure? We see group theory in many areas. So, for example, we have studied linear algebra, vector spaces. Vector spaces are nothing but they are all groups. They are groups plus some scalar multiplication and some properties. And then last semester you have studied rings. Rings also. What are rings? So rings are also groups plus multiplication. Here it was scalar multiplication. Here it is there is a multiplication also, and some properties additional. Right? Same way is there in fields also. Fields are also groups. It has multiplication uh, and some more properties. So it is multiplication. Yeah, so fields also we have a similar structure, and one more thing is algebras. This also you studied in linear algebra, right? Vector space theory. Algebra. What is algebra? Algebra is nothing but vector space and ring. An additional property connecting scalar multiplication and multiplication. Right. So that also underlying structure is common in this. Groups are there. This also has group structure there. This also has group structure. So they are the basic structure in abstract algebra. Secondly, that we can say that groups describe symmetry. So they describe because group describe symmetry. They have several applications in physics and chemistry also. They also study group theory. They have applications in computer science also, and in many areas. So group theory is just one of the uh, abstract structure which has lots and lots of application. So computer science also, and this is a part of application I studied when I was doing research, is that it has applications in cryptography also. Cryptography, again, it's a branch of cryptology. That means writing secret codes. So it has many applications in cryptography. It has applications in elliptic curves. These are curves which also have group structures. A lot of research is being done, and several applications of group theory are there. That is the reason we study group theory. Yes, so let us now begin with the definition of group. So, what is a group? As you have studied, this is just a revision only definition of a group. So, as in vector space, we start here also with a non-empty set. So, let G be a non-empty set. It's an any non-empty set, and with a binary operation. So, binary operation we denote by dot, or sometimes we also denote by star also. So, what is this binary operation? What do we mean by binary operation? So dot is an operation from, just like you have studied in inner product, right? So x cross x. So this is or we also, if we denote by star, we denote star from g cross g to g, but the resultant also is g. So we take two elements of g, a and b. So a belongs to g, b belongs to g. And how a dot b is defined? So this is defined as a dot b, a dot b. So a dot b is again an element of G, and if we denote it by star, then we write star of a comma b. This is when we take two elements, we apply a star on it. So this is nothing but a star b. This is another, again, an element of G. So this is binary operation, which implies closure also. So, but we, if we write as in terms of definition of book, then so which satisfies the following properties. So first property is for all a, b in G, a dot b belongs to G. Or we can say that a b belongs to G implies a dot b belongs to G. So we can write a b belongs to G implies a dot b belongs to G, and this is true for all a b in G. This is called closure property, or we say that G is closed with respect to this binary operation dot. Then second is associativity. Associativity, we take any three elements in G, A, B, C in G. This implies A dot B dot C equals to A dot B dot C. This is for all A, B, C in G. And this is called associative law. Right? Associative law. Then third is there exists an element E in G. There exists an element E in G such that A dot E equals to E dot A equals to A for all A in G. For all A in G, there is fixed E. So this E is fixed. It does not depend on A. So even if I take A1, E is fixed. A1 dot E equals to E dot A1 equals to A1. If I take A2, again E is fixed. So this is fixed. And this property is called existence of identity. Existence of identity in G. In G is important because E belongs to G. E should belong to G. The element E must be an element of G. It should not be anywhere outside G. And then again, for every A in G, there is an element which we denote by A inverse. This is just notation. So A belongs to G A can be anything. It can be a number. It can be any element. It's just a notation. A means it's an element of G. Just notation. So this is also a notation. A inverse does not mean 1 upon A. A inverse does not mean minus A. It depends on the binary operation and the set, whatever it is. But this is notation. That means it is inverse of A. What do we mean by inverse of A? So there is an A inverse in G such that A dot A inverse equals to A inverse dot A equals to E. So now A inverse depends on A. So for every A, there is A inverse. See the difference? Notice this. First we are writing for every A in G, there is an A inverse. So if I take A1, I have A1 inverse. If I take A2, I have A2 inverse. So for every element, there is inverse. So that depends on the element, chosen element. But here it is different. There exists an element for which this holds for every A. So there exists for every. So this means E exists for every A. It is fixed. Here for every A there is one element. Right. So understand the difference, and then this property is called existence of inverse in G. Right. So these are the four properties. Right. So what we take is we start with a non-empty set G, and there are four properties. G is closed with respect to this binary operation, that is an operation from G cross G to G. So this binary operation itself means closure property. That means if I take any two elements in G, I operate them, this product, the resultant also is in G. Sometimes we denote by star, sometimes we denote by dot. Here we denote by dot. Dot does not mean product. It means whatever the operation is. It can be addition, it can be subtraction, any operation. We just denote it by dot. Or some books also denote by A star B. So, and eventually we are not going to write this dot also. We'll just write AB. AB does not mean again product. What AB means is just A dot B, A star B, or whatever the operation is there, A times B, whatever that operation is there. So it does not mean product, but we'll just write AB. So right now we are just denoting by A dot B. So closure is there. For any three elements ABC is there. First you take operate A and B. The resultant you take operation with A is same as A dot B first, and then the resultant product, again not product but the binary operation with C. So that is called associative law. And third is there is an identity element in G. So existence of identity, again what is important is in G, this should be in G. So for every A, and for every A the inverse, existence of inverse for every A in G. So any non-empty set with these properties is called a group. Yes, also note that here we have used N. So here also there is A inverse. There is this. We have not used the. Actually, the identity element is unique, but we have not proved here right now. So we have used there exists an identity element, but otherwise E is the identity in G. That is what we'll use later on when we prove that identity is unique and every element has a unique inverse. When we prove that, we will show that we'll just write that E is the identity of G. A inverse is the inverse of A in G. Yes, so before we look for examples, why these properties? Why only these properties? So, what is the motivation behind defining such an abstract structure group? Why do we call a non-empty set with only these properties as a group? So, let us consider some motivation behind defining group with behind this four properties. So it is actually what we are using this property is when we solve an algebraic equation. So suppose we have just a simple equation in algebra like this. Let us say x plus 5 equals to 8. Something like this we have. Only one operation, addition is there. And in school, if you remember, how do we use to solve this? We take 5 on the other side. So that becomes minus 5. But what is that? Taking 5 on the other side It's not that we are taking 5 on the other side, but what we are doing actually is we are adding minus 5 on both sides. So this is 8 plus minus 5. And then what we do is we take this first, 5 plus minus 5, and then 8 plus minus 5 is 3. And then what we do, 5 and minus 5, they get cancelled. So x plus 0, this is 3, and x equals to 3. So this is how we take the solution, right? Right. So suppose we want to solve this equation in the set of natural numbers n. Is it possible? No, it's not possible. Even though x equals to 3, the solution is a natural number, but this is not possible. Why it is not possible? We are just taking only one operation, addition. There is no subtraction here. So addition. So what we are adding here? We are adding minus 5. Minus 5 is not there in natural number. So this is not possible. So we consider z integer. Minus 5 is there, of course. Yeah, then we can consider, then this is also an integer. But what actually we are doing here, when we are adding minus 5, what is this minus 5? Here it was 5, so we wanted to cancel it out. So we added minus 5. This is nothing but it is inverse property. 5 was there, so we added minus 5. So that means inverse of 5 is added on both sides. Again, whatever the resultant is there, the resultant is an integer. So that means we also used closure property. Whatever the resultant is there, that is an integer, closure property. And then here x plus 5 was there already, we added minus 5. What we got? X plus, and what we used here is nothing but we have taken, instead of this two addition first, we have taken this two addition. We know that it is going to be the same answer. What we have used is associativity. So here also we have used associative property. And then 5 plus minus 5, what we get is 0, that we know. Again, it is a closure property. But then what we used, we wanted x, so we eliminated 5 here. So x plus 0 is x again. What we used here is that 0 is identity. When 0 is added to x, we get x. So these are the properties which we actually use here. Closure property, associative law, existence of identity, existence of inverse in obtaining solution of such an equation. We can consider one more example with multiplication. Suppose like this, 2x equals to 12. Now how do we obtain x? So here there is one operation we have used, here addition, here now just multiplication. Similar example. So what we do, we want x, so we eliminate 2. Now there is multiplication, so there is no minus 2. So what we do is we multiply 1 upon 2, right? 1 upon 2 and then 2x. Both sides we multiply 1 upon 2. So what is this 1 upon 2? This is actually inverse of 2. So inverse exists. So can we now use integers? No, we cannot use integers. So let us use q. Here also we can use q, r. We cannot use natural numbers. So here we can use q, r also. So and then 2, then we use associative law. So that is 2, 1 by 2 times 2 first. Multiply that, and with x, this is equals to 6. Again the resultant closure. So again this is 1 into x. Now this is multiplication, so identity is 1, not 0. And so again that is x equals to 6. This is the solution. But again every element should have inverse. If we take q or r, they do not have inverse. 1 by 0. 0 does not have inverse. So we take q star or r star, set of all non-zero rationals, set of all non-zero reals. So for that this works. So these are the 4 properties actually we are using when we solve an equation. So that is the reason, that is a motivation that such a structure is required. Non-empty set, not only just non-empty set which satisfies these 4 properties. Why these 4 are chosen? The reason is this, what we have discussed. So that is one reason. Another reason is our clock, our watch. This is also a group which we don't realize also. Analog watch. Forget AM, PM. but then what we have is something like this. It's not a perfect circle, but anyway, I'm not going to sell this watch, so it is fine. It's my watch, right? So this is our analog watch, and forget AM PM. So just it shows time. It's bad time to study group theory. Uh, yes. So suppose it is 2 o'clock, right? So or whatever time it is. So 2 o'clock, then three, then four, and then so after 12. If it is 1 hour after 12, so what will be 12 plus 1? So we have a set of integers. So what we can see here, it is 1 to 12. So 1, 2, 3, and so on, 10, 11, 12. So this is what we see. And then this is our set G, non-empty set. And now we want to form this into a group. So after 12, 1 hour after 12, what is that? So that is not, that is 13, but 13 is not in the set. We want to be in the set. So what operation we define? We define an operation called modular. So modulo 12. So here we take modulo 12. This is our binary operation. So we also denote like plus 12. So addition modulo 12. So addition modulo 12. So this is nothing but 1 mod 12. So 12 plus 1, 2 hours after 12. So that is nothing but 2. 12 plus 2, that is 14, but that is 2. Then 3 hours after 12. So 15, that is 3. This is 16, and so on. Right? So this is closure property. Then what about identity? So suppose the clock shows 2 o'clock. Then the same position, how it will come? So either we don't make change at all, that means we add 0. So 2 plus 0, so we get 2. Another thing is that we rotate this entire watch, because it rotates in one direction only. Let us consider only clockwise direction. So what happens? We take 12. We take an entire rotation. So add 12, so that is 14. So then again also it will show only 2 o'clock. So that is 14 is nothing but 2 more 12. Again, if you come after one day, 24 hours. If the time is 2 o'clock, again, if you come after 24 hours, this is 26. But if you see the face of the clock, it will be again showing 2. So that means, if we have a dial and if we can rotate anti-clockwise for 12 hours, again it will show 2 only if we rotate on the reverse direction. So even if we have minus 12, that also is minus 10, but minus 10 is nothing but again 2 more 12. So all these are identity element, because 2 o'clock the clock will show same thing if we do all this. So what should be the identity? Identity is nothing but now it is a class. It is also 0. It is a class. So it is 0, it is 12, 24, 36, and so on. So minus 12 and so on. So identity is nothing but 0 bar. So all these are class. So what we do is, now we don't take 12. So instead of writing 12 here, what we do is take v0. It's just some motivation in behind this. Also there is a group structure. This is what I'm trying to explain. So 0 to 11 now we have. So we know our clock does not mention 0, but this is nothing but 0 for us. Now 0 to 11, and we have addition modulo 12. And inverse also same thing. What is the inverse of 2? Suppose the clock moves in the positive direction only, there is no negative direction. So 2 plus what we know is minus 2 will give us 0. But what is minus 2? Minus 2 is nothing. Instead of moving clock backward to 0, if we move forward, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So if we take 2 plus 10, and then we again get 12, which is nothing but 0 mod 12. So every element has an inverse. There is an identity element, and closure property is also there, associativity also there. So here also that is a part of kind of number theory also, modular arithmetic. And this is nothing but it's a group. If we consider this set G, then G with addition modulo 12 is a group, right? So That is the reason why we study all these four properties. So now we are interested in such non-empty sets which satisfy all these properties. So now let us consider examples. Right. So now we come to examples. So we investigate whether these are groups or not. So I write, we are not just writing examples, we are investigating uh, whether these are group or not. So let us take G equals to non-empty set to be n, and binary operation dot equals to addition, n with addition, whether it is a group or not. So first thing is that we have to check, first property is a and b are in n. If a and b are natural numbers, then it should imply that the operation we are taking addition, a plus b also is in n. This is true. Then associativity, first take any ABC, first take a plus b and then add c, and otherwise you take b plus c first, add this to natural number and then add this. The resultant will be same, we know. So this is also satisfied. But then the problem comes when we want an in identity. So what should we add to a so that we get again same a? So I'm going just quickly because you have seen already in BSc. If you have not seen, just go through this again. Pause this video if you want. Work it out. So a plus what element? So usually it is 0. A plus 0 it is this. But remember 0 is not in the set. 0 exists. A plus 0 equals to a. But what we stated in the properties, identity must exist in the group. So 0 is not in n. So identity does not exist. So this is not a group. Right? But then we can consider, instead of this, we can consider G equals to Z. So if we take G equals to Z and addition, then this is clearly all this property hold. If a and b are integers, a plus b is again an integer. Associative also holds, a plus b plus c equals to a plus b plus c. And then 0 also is there, a plus 0 equals to a, and 0 belongs to z. So identity now is in the set. And what about inverse? Inverse also we know a is there. What should we add to the a that we get identity 0? So inverse of a, additive inverse is nothing but minus a. Minus a is also there. Here also inverse was not there. If I take 2, there's nothing which gives me identity. Anyway, identity is also not there. So first what we have to verify in that order, identity is important. Then only we check inverse. If identity is not there, there is no point of checking inverse, right? And but this one, integer, set of all integers with respect to addition. So this forms a group. So this is a group z with addition. So this forms a group, right? So we consider more examples. Yes, so let us consider, I'll give you some exercise to verify for your practice, which we'll discuss in the meeting, in our Google Meet. So this is for your practice. So check first one, check integers with subtraction. So G equals to the set of integers and with subtraction, whether this is a group or not. Similarly, check set of all rationals with addition, set of all rationals with multiplication, uh, set of all reals with multiplication. If these are not group, then what is a group? I mean, what should restriction should we put to make this into a group? That all we'll discuss in the meeting. Uh, yes, some more further examples. Consider set of 2 cross 2 matrices. So take M2R, set of all 2 cross 2 matrices over R, real entries, and take matrix addition, whether this is a group or not. Similarly, take M2N with addition, right? Or let us take M2Z, because N will not be a group. Check this, M2Z with addition. Then, sorry, seventh one. Then take M2Z with multiplication, eighth m to r with multiplication. Right? So these are some very easy exercises which you can check whether they are in a group or not. They form group with this or not. This multiplication here are matrix multiplication. These are matrix addition. These are usual rational and real addition, that real numbers multiplication. Sorry, and this one is important. So this is an important exercise. We consider S is any non-empty set. So that is S is any, it's any non-empty set, general setting. So S is any non-empty set, and G is the set of all functions from S to S. G is the set of all functions from S to S. So we have a non-empty set S, and S to S we consider set of all functions. Right? So any element X is there, Fx again is in S. So we have functions from S to S. So now we want to give a binary operation on G. What operation should we give on G so that it becomes a group? Right? See, our set is G. Set is not S. S is what? S is just any non-empty set. It's not fixed. We cannot take S to be a set of natural numbers or anything. It is just any non-empty set. Now what our set is, which we want to form into a group, the set is G. It is set of all functions from S to S, where S is a non-empty set. So on functions, how many operations can we define? So let us first list all these operations. So what easily comes to mind is f plus g. If f and g are two functions, f plus g is a function. How it is defined? F plus g at x. F plus g is also function from, if f is function from S to S, g is also function from S to S. F plus g is also function from S to S. And f plus gx is defined as fx plus gx. These are just some operations we are listing. So once addition is there, of course, the next thing comes into mind is f minus gx. How f minus gx is, f minus g is defined? Difference of two functions, f minus g at x equals to fx minus gx. This is another operation. Yes, and then multiplication, f star gx. How this is defined? Fx into gx for every x in S. Of course, then yes, you have got it correct in your mind, f upon gx, but then you have to worry about something. What is that? Fx upon gx, where gx is non-zero. So this cannot be defined always. It depends on the set. It depends on what x we are taking. So these are some operations on, yes, and one more thing. Some of you might have thought here some different operation. What was that? Not just usual multiplication, but that is composition. F is a function from S to S. If I take any x here, f of x is again in S. I apply g. So g of s again is an element of S. So I can take g of x, g of f of x, which is nothing but g of f of x. This is for all x in S. So these are some operations. You can think of further operations if you know. Any operations on function, if you know, you can also list them. And now S is any non-empty set, G is set of all functions from S to S. And check all these operations, whether any of these operations together with G forms a group or not. So these are those exercises which I want you to try. You can think about other examples of group also. But as I always say, while thinking of examples, do not try to recall. Just think of some set, think of some operations which are well known to you. Try to think of some more and more sets and more operations, and then try to verify whether they form a group or not, just for your practice. Do not recall what you have studied in B.Sc. Do not try to remember. Right? So we are going to discuss in our meeting, actually, that is the first class. This video is for pre-preparation of that class. And so I hope you go through this video again carefully, check all these things, and we are going to discuss when we meet. Okay, so I should stop here. See you. Thank you.